Hey, AP Chem. It is time to finish the thermodynamics unit. I'm actually pretty excited about this. The very last topic that we need to discuss is something called Gibbs free energy. Now, we just learned about two different thermodynamic values, entropy and enthalpy. Enthalpy is delta H. We know that that's essentially how much heat is flowing into or out of a chemical reaction. And then we also know about entropy. Entropy is essentially the measurement of the order or disorder of the system. And we also know that that takes a certain amount of energy. Order is not natural. Disorder is essentially what the universe is automatically moving toward. So we, the scientists, we, the humans living in the universe, need to expend energy to try and push order onto the universe. That takes energy. So thermodynamically speaking, we need to account for that to try and figure out whether or not a chemical reaction is spontaneous or non-spontaneous. And again, spontaneous essentially means that the reaction is going to go without a whole bunch of outside intervention. You won't necessarily need to do a whole bunch of anything to try and get that reaction to do what it needs to do. And this is the purpose of Gibbs free energy. It takes these two thermodynamic terms and it puts them in context with each other to try and figure out where is that balancing point. Do we have enough enthalpy that it can outweigh entropy? Or is there such a large entropy gain that it doesn't really matter about the enthalpy? I know that this all seems pretty confusing just by talking about it. So I think, why don't we switch over to actually taking a look at a couple different types of calculations. Okay, well, I'm hoping at this point that you're able to see my whiteboard just a little bit more clearly. So let's move forward again a little bit here. So again, Gibbs free energy is essentially talking about the balance between these two different thermodynamic forces. We have enthalpy, which is delta H, and entropy, which is delta S. So looking at the balance between these two forces, we know that when delta H is negative, we have an exothermic reaction. And when delta H is positive, we have an endothermic reaction. We also know that the sign of entropy really can matter. So when delta S is positive, that means that we're moving toward chaos or disorder. And when delta S is negative, it means that we're moving toward order. Now, nature really favors two different thermodynamic states here. So as far as the enthalpy of a chemical reaction is concerned, if it had to pick one of these two, exothermic or endothermic, it would pick an exothermic overall chemical reaction to be more of that spontaneous style. So there are way more spontaneous exothermic reactions than there are endothermic. However, there are still spontaneous endothermic reactions. We just need to make sure that we have a balance between these two forces. And also, we do know that thermodynamically speaking, nature would prefer delta S to be positive. It really needs to have the overall chaos of the universe increasing. So it really appreciates a positive delta S value. Now again, Gibbs free energy is almost the exact same thing. It is simply a thermodynamic term that puts us in the position of understanding through its sign what's happening with the overall chemical equation. And we're going to calculate this and put this in terms you can understand in just a minute. So we have Gibbs free energy, which has a symbol, delta G. Now, you'll find on your thermodynamic tables that I shared with you yesterday that there is a third column of delta G data on that chart. That's going to be pretty important for you to dig into. So overall, Delta G can be negative, delta G can be positive, and delta G can be 0. All three of these different conditions imply something pretty specific thermodynamically about your chemical equation. When delta G is negative, you are going to be dealing with a spontaneous chemical equation. So that reaction will proceed on its own without very much intervention at all. You won't have to force the reaction to proceed forward. When delta G is positive, you have a non-spontaneous chemical equation. So essentially, you've got to bring everything in your arsenal to try and get that chemical reaction to go. And most notably, you're really going to have to change the temperature to try and get this to switch over to spontaneous. More on that in just a moment. And when delta G is 0, it's at this magical tipping point between being spontaneous and non-spontaneous. And there's only one very specific temperature at which this state will actually occur. Well, we're going to call this equilibrium. And this is going to be really extremely important for you to remember as we move forward with the remainder of our units in AP chemistry. Now, there's a couple different ways that you can actually calculate the Gibbs free energy. In fact, I'm going to show you two different ways that we can go about this. But again, what's really important is to remember the different signage here of your delta G and what that implies about the overall chemical reaction. Maybe I have enough room that I can keep this on here. We'll give that a shot. Okay, so the first way that you can actually calculate Gibbs free energy is to use delta G data from an appendix. And this is probably going to be your favorite way because I hate to say it, this is the simplest way. I'm going to show you a totally new and unfamiliar equation. You've never seen anything like this before. The delta G of the reaction is equal to, I know, get ready for it, the sum of the moles of the delta G of the product minus the sum of the moles of the delta G of the reactant. Now, we've done these calculations several different times. I don't think that this comes as any specific surprise. But what I think might be a good idea for us to do is to do a sample problem. Now, we had been working with this equation yesterday. We had 2NO2 gas forming N2O4 gas. And what we're really looking for is this reaction spontaneous? Well, let's find out. Now, while I'm erasing this, I'm going to point out something actually pretty important. The standard values that you're going to get in the table that I gave you are all listed at 25 degrees Celsius. That's going to be really, really critically important as we move forward with the second style of calculation. But for right now, just know that they do occur at 25 degrees Celsius, essentially a little warmer than room temperature. So essentially, this really should say, is this reaction spontaneous at 25 degrees Celsius, to be completely accurate. Now, I did a little prep work for you, and I looked up the values for G in the appendix. The NO2 had a value of 51.30, and the unit on G is kilojoules per mole. And the N2O4 is 97.82, and again, that's in kilojoules per mole. So as we go to set up our chemical equation here, or at least our calculation, delta G reaction is going to equal the sum of the moles of the product. Well, for us, that's just N2O4 minus the sum of the moles of the G of the reactant, and that would be 2 times our value for NO2. So now it's just a matter of plug and chug. So our value here would be 97.82 minus 2 times 51.30. And when you go and plug and chug this into the calculator, I found the answer to be equal to negative 4.78. And again, the unit is kilojoules per mole. So we've got a negative value for delta H, not delta H, delta G. What does that mean then? Well, at 25 degrees Celsius, that this reaction is spontaneous. So overall, really not that terrible to calculate the overall delta G of a reaction, just simply using the G data that's actually given in the appendix. So there is a second way that we can actually figure out whether or not a reaction is spontaneous or non-spontaneous. There's actually a secondary equation that we can use, and it's actually quite nice. This is the one where entropy and enthalpy really come into play. Here's the equation. It is that delta G is going to equal delta H minus T delta S. So what this essentially does is it actually proves here that Gibbs free energy is a balancing act between enthalpy and entropy. And it's really critical also to note that temperature will affect whether or not our overall chemical reaction is going to be spontaneous or non-spontaneous. And that just makes sense in a thermodynamics chapter that we talk about temperature and available heat essentially around the reaction to do what it needs to do. So I really want you to kind of look at this very, very carefully. Remember that what's favorable is we would really like delta H to be negative. I'm just going to like favorable is a negative delta H and a positive delta S. This means exothermic. This means chaos. Now, if you're really careful here, when you go to plug this in, what you're essentially going to see then, get another color pen here, is if I put in a negative delta H and a positive delta S, what you're essentially going to have here is a negative minus a positive. So this is just more negative. Okay, I'm hoping you can see that mathematically, that this term then is also negative. Delta G has absolutely no choice but to come out also being negative in charge, which means that when you have an exothermic reaction that's also moving toward chaos, it doesn't really matter which temperature you're going to plug in here, they're always going to be spontaneous because both of these terms are always going to be negative. There's another combination of values that I think is valuable to kind of take a look at, because now we can actually just kind of predict from delta H and delta S data whether or not our reaction is spontaneous or non-spontaneous. There we go. Well, what if we flip these values around? What if we go with completely unfavorable conditions? So what would be completely unfavorable? I'm going to write a little note here. Always delta G minus spontaneous. So unfavorable would be a positive delta H, meaning an endothermic reaction, and a negative delta S, which would mean that it's moving toward order, and that takes energy. So let's see what those values would look like if we would plug those into my equation at the top. Okay, so if I would plug in a positive delta H value, and if I would plug in a negative delta S value, a negative times a negative terms this whole term positive. So this is a positive and this is a positive. There's no choice here. Delta G is always going to come out to be positive. So delta G is always going to be non-spontaneous. So always delta G is positive and non-spontaneous. So there must then be some other magical combination, because quite honestly, these aren't the only two combinations of both your entropy and your enthalpy. We always are looking at what is the balancing act between these two forces. Sometimes our entropy can be so large that it won't matter what, our enthalpy value can be so large that it won't matter what we're putting in for our entropy. And the same in the reverse direction as well. Sometimes that entropy value is so large that it won't matter what we're plugging in for our overall delta H. Essentially what that means is for some of these combinations, we're going to need to calculate this. And let's make this just a little bit more user-friendly here. And let's take a look at what this could look like in a chart. So overall delta H values, overall delta S values, and what they're going to end up being, spontaneous or non. We can have delta H be negative or positive, negative or positive. And the delta S that can come along with that would be, let's see, positive, negative, positive, negative. I think those are all of the different combinations. Okay, so again, there were two combinations that are always going to be guaranteed to give you a certain answer about whether or not you're dealing with something that's spontaneous or non-spontaneous. And that would be, one of these would be right here. The negative delta H, that's exothermic, favored by the universe, and positive delta S, that's moving toward chaos, and that's also favored by the universe. So this is always spontaneous. And the complete reversal of that, a positive delta H and a negative value for delta S, is always going to give you a positive delta G value. This is always non-spontaneous. Whereas these combinations, if you have a positive value for delta H and delta S, or a negative value for delta H and delta S, well, now you've got a competition, because we have to see which one of these values is larger as to what sign our final answer is going to be. And the magic about this is really the temperature. So in both of these cases, it's temperature dependent. Because when temperature is large, it gives entropy a little boost. But when temperature is small, or when it's low, it basically devalues entropy's kind of hold on the overall chemical reaction. It gives enthalpy a chance to shine. So we really need to look at temperature and its relationship to this overall chemical reaction. I know that that's kind of a lot to take in all at the same time, but whew, it is very, very important. Now, taking a look at this, there's essentially then two relationships that we're going to want to make sure that we're pretty sure of. So what we can do is plug and shove values into this equation to be able to figure out one of two things. So first of all, I can plug in a temp to see if the reaction is spontaneous or not. So I can plug in a temperature to calculate the G, or the reverse. I can plug in a G to find the temperature at which the reaction becomes. spontaneous. And this is where a really important piece of information comes in here. When delta G is negative, we know that it's spontaneous. When delta G is positive, we know it's non-spontaneous. So really, there's only one value of delta G that will show you the borderline between being spontaneous and non-spontaneous, and that's when delta G equals 0. So we can plug in a value for delta G equals 0 to find the magical temperature where our reaction is going to switch between these two states, between being spontaneous and non-spontaneous. All right, so again, I think it might be beneficial to go through a sample problem to actually see what this looks like. I want to go through example number 1 first, to plug in a temperature to see if the reaction is spontaneous or not. So let me get rid of this down here, and let's look at a very specific chemical reaction. Why don't we look at the reaction of CO gas plus H2O gas will form CO2 gas plus H2 gas. I'm going to give you some thermodynamic values. Delta H for the reaction is negative 41.2, and what's really important here are the units, kilojoules per mole. And the delta S for the reaction is negative 135, and again, what's really important about this are the units. This is in joules per mole Kelvin. Now, again, unit agreement is going to be the deciding factor here between one grade and another for us. Notice that the unit for the delta H is in kilojoules, but the S is in joules. We need to make sure that these two things have unit agreement to be able to plug them into this equation where we're calculating these delta G values. Otherwise, they're going to be kind of out of whack. So a lot of the times what I'll do right out of the gate is I will actually transform my S value to be in units of kilojoules. Now that would mean to divide it by 1,000. So I can rewrite that. Delta S reaction is negative 0.135. My unit is now kilojoules per mole Kelvin. This is the value that I want to use against this delta H. All right, I think it's time that we start thinking about plugging and chugging. So our delta G of our reaction equals delta H, that's negative 41.2, minus the temperature. And by the way, I should probably have mentioned that this is at 25 degrees Celsius, so that's 298 Kelvin. Temperature has to be provided if you're trying to calculate the G. You can't have two variables in this equation. Okay, so that would be 298 times our new S value, that's the negative 0.135. And again, we want to make sure that we have that unit agreement, kilojoules and kilojoules. All right, now we plug and chug, and we find out that at 25 degrees Celsius, the delta G value, it's not very impressive, but it's negative 0.97, and that's in units of kilojoules per mole. What's most important is we have this negative value, which means it is spontaneous at 25 degrees Celsius. So I actually really like this approach. I like that you can actually use your two thermodynamic values, your enthalpy and your entropy, to try and calculate whether or not that chemical reaction is spontaneous. But like I promised, there's actually a second purpose to this equation. So in this direction, we plugged in a temperature to be able to figure out whether or not the chemical reaction was spontaneous. But the second use of this equation is to plug in a delta G value and calculate the temperature at which you're going to get that desired result. So again, the second purpose of this equation is to calculate the temperature at which the reaction becomes spontaneous. Okay, we're going to look at that same equation again, so we can use these same thermodynamic values. So we're going to look at CO gas plus H2O gas will form CO2 gas and H2 gas, and our delta H for our reaction is still going to be negative 41.2 kilojoules per mole, and our delta S of our reaction is still negative 135 joules per K mole. And don't forget that you really still want to make sure that you're converting this number into kilojoules for unit agreement. So that's negative 0.135 kilojoules per K mole. If you're going to make any mistake, this is where it's going to be, because essentially everything else here is just plug and chug style math. Okay, so in the equation, delta G equals delta H minus T delta S. I have delta H, I have delta S. I'm trying to figure out the temperature in this reaction, so I better know a delta G value. Well, again, the delta G value, that magical switching off between the reaction being spontaneous with negative delta G values or non-spontaneous with positive delta G values, there's only one value left, and that's 0. So the big thing to remember about this style of equation is to plug in 0 for delta G. So if you're asked to calculate a temperature, you want to plug in a 0 for that delta G. So 0 equals negative 41.2 minus temperature times negative 0.135. Again, use that kilojoules for that unit agreement. Plug and chug, come up with our temperature. Temperature comes out to be 305 Kelvin. 305 Kelvin. So 305 Kelvin is the tipping point between the reaction being spontaneous and non-spontaneous. So I want us to think very carefully about this. So we have a negative entropy value. Now, that's not favorable, but we do have a negative, entropy value is negative. Our entropy value is negative. Our enthalpy value is also negative, and this is favorable. So essentially what we want to do is to find temperatures to try and keep this thing being spontaneous. We want temperatures which devalue our entropy term. At temperatures above 305 Kelvin, what you're going to find is that, you use a different color. Right here. So if we plug in huge values for our temperature, then this overall term becomes very, very positive, and it's going to overwhelm our negative enthalpy value. That's going to end up giving us a positive delta G. But if I plug in very, very low temperatures, this might be positive, but it's not going to be as positive as this term is, and we'll end up with negative delta G values. So for temperatures 305 and above, this is non-spontaneous. And for 305 and below, it's spontaneous. These problems do involve a little bit of thought work. You have to be very, very careful, not only with your units, but also your signage. But I think after you kind of get a couple of these under your belt, these really aren't going to be that troublesome.